Okay, thank you, everyone. I'm Henry Zangaro. I'm one of the developers on the JIT optimization and x86 code gen team under Andrew Craik. I'm going to be giving a sort of 30,000-foot view of escape analysis with some details on some of the things that it does. Escape analysis is one of the optimizations in OpenJ9. Before I go on, I'll just flash this slide about disclaimers. Don't make plans based on this presentation. Don't. There's nothing guaranteed in this presentation, etc. Thank you. Okay, so now that that's out of the way, just a brief agenda here. So this is what we'll be going over. I'll start off with some motivating examples describing the situations in which escape analysis applies and describing what it means for something, an object in this case, to escape, and what escape analysis does with that information, and what benefits it provides, and some of the things some of the techniques it uses to deal with escapes when they do happen. And then I'll go on to describe some recent improvements that have gone into escape analysis over the last year and a half or so, and a little bit of performance results. Okay, so motivating examples. So just one thing I want to say about the examples that I'll be showing. Some of these examples might appear like they're sort of contrived or artificial, but that's just because they're simplified for the purposes of presentation. But the situations that they describe really arise in actual Java code or byte code that's more involved, and escape analysis will have the effect that we desire. So moving on to an actual example, if you consider string concatenation in Java, so for instance, I've got an integer, a primitive int, and a couple of strings that I'm concatenating to one another, and then printing out the result. In the Java-C compiler, emulates the substrings onto that string builder, and then finally calls toString to extract the final string object from that process. So the equivalent Java to the byte code that's actually generated looks something like this. It can, as I said, constructs a string builder, does several append operations for each of the values being appended to the string, and then calls toString to get the final string object. So the point here is that this string builder that's being created is only used for the duration of this single statement and only within this particular method. So it's a very short-lived thing. It's needed only very briefly. Second motivating example. Quite often with abstract APIs in OO programming languages, the APIs that people use that are provided by the system or that are provided through third-party libraries, whatever, they're very high-level abstract. They tend to make programs very easy to understand and maintain, and that's the purpose. But they also often result in very many very short-lived objects. So, for example, iteration over items in a collection. So here we've got an array list that we're iterating over. We're extracting, the array list contains integer objects. We're iterating over them and extracting each value and computing the sum of them. But the interesting thing is that here under the covers, Java-C, although it could be an explicit call as well, is calling the iterator method on the array list, and that ends up creating a array list $iter object, which is just used for the duration of the loop, simply to go through the contents of the array list and return each value to the program. So again, another very short-lived object. A third example comes up in the context of boxed primitives in Java. So quite often, when if users are doing something with primitives that they need to store into more general purpose data structures such as hash map or list in Java, they have to actually box those and create objects, integer objects or double objects or what have you. But those instances are, again, often needed only very briefly. So here, for instance, we've got a hash map that has a that contains a dictionary, and it happens to be mapping from the lengths of words to strings that are that length. And in this particular case, when I'm given a primitive length, I need to get an integer object that has that as its value, has that length as its value in order to look up the words of that length in the dictionary. So again, I'm creating an integer object here. It could also be done through value of, but the point is that we're getting an integer object that's created simply to look for the hash map entry, and then it's discarded. It's not stored anywhere or used. So in very many cases, as I was saying, Java programs end up creating objects that are needed only very briefly for a brief portion of the duration of a method, or even more briefly than that within perhaps a single statement. Ordinarily, per the JVM spec, these short-lived objects would ordinarily be allocated on the heap and cleaned up by garbage collection, were it not for escape analysis. So here's where escape analysis comes in. The purpose of escape analysis, or EA, is to identify objects created during a method invocation that do not actually escape. So what does it mean to escape? To escape means that the object is exposed to another thread or outlives this method invocation. So we want to find the objects that do not get exposed to other threads during a method invocation and that do not outlive this method invocation. So what are some of the means by which an object can escape? Well, the most obvious one is via a return from a function. So for instance, in this example where I've got a modular integer class, the successor method in this class is constructing an instance of modular int based on the current instance. It's finding the next value modulo the modulus. So the successor method returns that newly constructed modular int, and so that modular int is considered to escape from the call to successor. It's made available to the caller. Another, probably fairly obvious now, once you've seen that example, case where escapes might occur are in the context of assignments to fields or elements. So if an object can be accessed, if it's stored someplace where it can be accessed after the current method invocation, such as I said, in an instance field, a static variable, or array element, then that's considered to be an escape. So for instance, I've got this point class which describes a point on an XY coordinate system. And given some other object, I've got a set location method that, given coordinates, sets the location field for that object to be a new point object that has those X and Y coordinates. This point object can now be accessed after we return from set location through the loc field of this object. So that is considered an escape. And a third common case in which escapes occur is via arguments to a call. So if an object is passed as an argument in a call in a method, or it's used as the this pointer in a call, that can be considered to be an escape as well. So the thing is being passed to the method, passed to a method, it might be used in some other fashion, like being stored in a field or what have you, stored in some data structure. So in this example, we've got a hash map. We are constructing an integer object and storing it to the hash map using map.put. So it's an argument it's passed as an argument. We know, based on the implementation of HashMap, where this thing is going, but the point is, in general, it could be going arbitrary places, stored in data structures or what have you. In this case, it gets put into the HashMap and can be retrieved by subsequent calls to map.get. But I'll mention in passing here that there's something called peaking that escape analysis does that can be used to mitigate some of the things that might happen through argument call, through passing an object to a pointer, and similarly inlining and other optimizations. But we'll see that in this next slide. So even though I described some pretty broad conditions under which things are considered to escape, you actually have to think about things in a broader context. So something that, given optimizations that the JIT might apply, some things that might look from the Java source to escape might not actually be considered to escape from optimized code. So again, if we consider this modular int class that has a successor method, as I said before, the successor, the newly constructed modular int, is going to be considered to escape from the successor method. But in the context of the +2 method, where we have 2 calls to successor, the first call to successor simply uses the result of the first call to the +2 first call to successor simply uses the result of that and calls successor on it as well. The first modular int that's created within the context of +2 does not escape from +2. It's used entirely within that context. So if both of those calls end up being inlined, only the second modular int that's being constructed within the broader +2 context is considered to escape. So if you take a look at how this code might look when it's inline, that becomes a little more clear, or a little more obvious. So now we've got the first call to successor resulting in an object that's being constructed, and the second call to successor is now creating a second modular int based on the values of that in the fields of that first object, and that second object is the one that's actually returned from the context of +2. Okay, so now I've described all the different things that can be considered escapes. But what does EA actually do with any of this? Well, the main purpose of EA is to determine situations in which objects do not escape, because objects that do not escape a method invocation, EA is able to allocate those things on the stack. So for instance, if taking my modular int example again, after inlining I showed that ends up looking something like this. After escape analysis, this ends up turning into something like this, where the first modular int object that's being created here is allocated on the stack within the +2 call. So I've shown that here with a pseudo op named stack new, just to illustrate that this is allocating space for this object within the method, but it's only at the point, and that allocation happens of the space happens when we enter the method, along with all the rest of the space on the stack for that method invocation. The fields are only filled out at the point, subject to optimization, of course, are only filled out at the point where they actually need to be initialized by the constructor call. So we hit the constructor call, we fill out the fields of that, in this case by calling the init method, the constructor method, or if it's been inlined, actually having the expanded fields be set through assignments. So what's the purpose of that? Okay, well, the point of allocating things on the stack is that it avoids the overhead of heap allocation. So space for any objects that are stack allocated is reserved as part of the call stack frame. That avoids the cost of garbage collection when the object is no longer needed. And in turn, the space is simply freed as part of the call stack frame upon leaving the method invocation. So it reduces some of the cost associated with allocating the object. It reduces some of the cost associated with garbage collecting the object when it's not needed. And there's also the possibility, although this isn't guaranteed, of improving locality of reference. If we've got several interrelated objects that are all being allocated on the stack, there's the potential that they're close to one another in memory and have less likelihood of cache misses and so on. Okay, so that provided a really quick look at some of the situations in which we've got short-lived objects, what escapes are, and basically what the goal of escape analysis is. Now we'll take just a slightly closer look, moving down from 30,000 feet to 20,000 feet, at what escape analysis actually does. So in going through analyzing the contents of a method, it looks for candidates for stack allocation. So it looks through for new objects. It looks for, new instructions, new array instructions, or a new array. So any of the situations in which we're allocating objects within the method or within inline code in the method. And it follows through the uses and definitions of the variables in an attempt to detect situations where those things might escape from the method invocation per the definition of escape that I was providing earlier. And it does that using the useDefInfo and value numbering that's available within the JIT for a method to track the uses of candidates. So it walks through the code looking at the useDef information, trying to determine which candidates actually might escape from the method. Any candidates that it determines do not actually escape will be allocated on the stack. And then it decides at the end whether it wants to request another pass if it sees additional opportunities or has opportunities that it has deferred for reasons that I'll describe later. It might then request that another pass of escape analysis be applied to try to clean up those or stack allocate those additional cases. One thing I should mention regarding stack allocation is the nature of the stack allocation. So the way the object is laid out in memory on the stack. So when EA stack allocates an object, it can actually allocate it in a contiguous fashion or a discontiguous fashion. In the case of a contiguously allocated object, it's laid out in contiguous memory with the fields all laid out as they would be for an object that's allocated on the heap. The reason that EA sometimes needs to lay out an object contiguously is that it might be used in a context in the generated code where a heap allocated object might also be needed. Or might also be accessible. So if a piece of code in the that's going to be ultimately generated might be referring to a stack allocated object, or it might be referring to a heap allocated object, the JIT has to lay out or EA has to lay out the stack allocated object in a contiguous fashion so that the memory layout looks the same, the JITted code runs properly on it. In the case of a discontiguous object, a discontiguously allocated object, the fields of the object are exploded into individual temporary variables. So that happens in situations where the generated code is not going to need to access either a heap allocated or a stack allocated object at the same point through the same generated code. So if it knows that it's only going to be operating with this stack allocated object, in all those particular locations where that object is used, then it can explode the thing into individual temporary variables. And that has the added benefit of avoiding indirection through an object pointer. Now it can refer directly to those variables directly on the stack. And it has the further potential that if there are fields in the object that are unused, it can discard them. And it also allows for additional optimizations to be applied to those temporary variables, such as general register allocation or dead store elimination, and many others. So that was a really high-level description of what it means for something to be contiguously allocated. Just to make it a little more concrete, consider this method where we've got something that's iterating over the entries in an array list that contains integer objects. And it's trying to find the maximum absolute value in that thing. So it starts off by constructing a max value that contains the integer 0. And then for each value in the array list, it checks is the current max value less than the absolute value of the next item in the array list. And if it is, then it updates max to refer to that new maximum. So in the context of EA, this integer object is considered a candidate for stack allocation. In going through and seeing where that candidate is used, EA notes that it's assigned to the variable max, but it also notes that another object that's not a candidate for stack allocation is also stored to that variable max. So max can contain both the candidate and it can contain some other non-candidate objects potentially. So as I said before, that implies that the max, because max has to be able to refer to both heap allocated and or stack allocated objects potentially, the stack allocated candidate in this case has to be laid out in contiguous memory. So it's laid out, as I said, in the same shape as a heap allocated object would be. Now, discontiguous. So here's an example in which discontiguous allocation might come into play. Here I've got my point class again, except this time the constructor happens to be also setting a distance from the origin field, just for purposes of illustration. So I'm constructing an instance of point, and I'm simply using that thing to get the distance from the origin, because that was the only thing that I was interested in. You can imagine a situation in which there's much more complicated operations going on in the constructor, and you might create a value, perhaps a calendar value or something like that, and pull out a single field or a small subset of fields. This is the sort of situation that this is meant to illustrate. So for the purposes of the method in which this constructor call is happening, this point object that I'm constructing here is considered to be a candidate for stack allocation. The candidate is simply assigned to this variable p, and the only thing that we do with it is extract a field from it. We never assign any other variables to this variable p. It can never refer to some other thing that might be heap allocated. So we know that if we stack allocate this point object, that it doesn't have to be allocated contiguously. It can be allocated discontiguously. So after applying EA inlining and EA to this thing, we end up with code that looks roughly like this. We have several temporary automatic variables, px, py, that's just for the purposes of illustration. In the actual JITted code, they wouldn't be named that way. But px and py that are assigned the x and y coordinate values, and a p dist from origin that is assigned the calculation for the distance from the origin, and we return that temporary p dist from origin as the result of the function. Then, as subsequent optimizations go through, they will actually be able to discard these assignments potentially to p underscore x and p underscore y and completely eliminate those variables as unneeded. So that sort of illustrates the point I was making earlier about about having additional optimizations being enabled, dead code being eliminated, etc. Okay, so I mentioned earlier about passing things into arguments and as arguments rather, and that we have the potential of doing something called peaking in escape analysis. So in our earlier examples, as I said, we saw how passing an object as an argument or as this object on a call is considered to be an escape for that object. But EA has the possibility of dealing with candidate objects that are passed as arguments, in many cases by peaking into the method implementation. And it can also peek through several levels of method invocation. So if method A, if EA peeks into method A and that thing calls method B, it can also peek into method B and so on to see how the argument is being used. So what's the purpose of peaking? Well, most method inlining occurs very early in the compilation. But suppose in this example, again using my modular int class, that I've got a getModulus method that simply returns the value of the modulus. And there's a typo here. The return M should actually be return modulus. But in any event, let's say I'm iterating through an array list that contains a bunch of modular ints, and I'm checking to see whether they all have the same modulus as some other modular int that I'm constructing within this method. So the modular int I'm constructing here is a candidate for escape allocation. But let's say that the getModulus method has not been was not inlined for whatever reason. So I said before that this would look like an escape to escape analysis, but in the process of peaking, EA can look at the actual implementation of getModulus and determine, in fact, that this object that's passed there does not escape. It's not being assigned to some random location in some other data structure or anything like that. It's simply getting a field. The getModulus is simply getting a field for from the object. So EA is able to then stack allocate this thing, the modular int. And so everybody's happy. And because the candidate object is being passed as an argument, or this pointer, on a method, that method could also accept ordinary stack heap allocated objects. So as I said earlier, that means that the thing has to be contiguously allocated. So it's the EA will contiguously allocate the modular int on the stack. And as an added bonus, EA will also ask inlining to attempt to inline getModulus at this point, because it's obviously potentially useful. It's an important method for the purpose of the checkmods method. Now, so we've seen a special case where escape analysis is able to deal with something that would ordinarily look like an escape through peaking. Here's another case where EA is able to deal with something that would ordinarily be considered to escape. and that's in situations where the escape happens in a cold block. So what's a cold block? Well, a cold block, roughly speaking, is a piece of code within a method that through profiling, it's been determined that that block of code is not frequently executed. Perhaps it's throwing an escape, throwing an exception, or doing some other rarely executed operation. If the escape of an object actually happens in such a segment of code, escape analysis can still decide to stack allocate the object, and it can mitigate that escape by doing something called heapification, which is allocating a new instance of that object on the heap at the point where it's actually escaping. So if that piece of code, that cold block, is never actually executed, then there's no harm done. If it is executed, the generated code is able to allocate the object on the heap at that point, and thus maintain functional correctness of the generated code. So here's an example where that sort of thing might happen in Java. So again, with our modular int class, let's say we have this candidate object within the loop. Most of the time we're going through and checking everything is okay, but let's say 1% of the time, or even less than that, the condition that's being checked here fails, and we end up throwing an exception. And this exception that we're constructing, it stores the value of curval, the candidate object, into a field in the exception instance that's being created. So it's considered an escape. Escape analysis, as I described, because that's an infrequently executed piece of code, will still go ahead, or might still go ahead, and stack allocate the instance. So as I described earlier, the space for it is reserved at method entry, and only within the body of the loop will the fields actually, for the modular int, that modular int actually be initialized. Then at the if and when an exception actually has to be thrown, the generated IL will construct a new instance based on the values that are stored in the stack allocated instance, and pass that to the exception that's being constructed and ultimately thrown. Heapification can also occur in other cases, and one of the most important of those is with guarded virtual calls. Again, this is a situation where you have a block of code that is, at least so far in the execution, infrequently, or in fact never being executed. So consider this example. I've got this run method that is accepting as an argument a use complex object, and on each invocation of the calc method of this use complex object, I'm constructing a new complex number that I'm passing as an argument to it. So this calc method, in this particular case, we only have one implementation of this method in existence at the point at which the compilation is happening, let's say. It's quite possible, in other cases there might be multiple implementations, but in this particular case, I've only got one use complex class in that class hierarchy. It's not been extended at all. There's only one calc method. So I know, or the JIT knows, the implementation of calc at this point. What it will do when inlining happens with that is it will generate code that looks roughly like this. It checks, has the method not been overridden? So has the calc method not been overridden? And if it has not, then it can use an inlined version of that method. And so the inlined body looks something like this, where it takes the real components and the imaginary components of the complex number and performs some operation on them. And that is the inline version of the calc method, and adds that to the total sum that's being computed. If the method has been overridden, we end up going into the else branch. Now, it hasn't been at this point in the execution, but sometime in the future, somebody might load a new extension of useComplex, a new class that extends useComplex, and it might override the calc method. So, as I said, as long as the calc method has not been overridden, the inline version will continue to be used. Now, what does EA do with that? Well, EA detects that it's got a case where an inline method is being invoked and it's not yet been overridden. It will treat the it will stack allocate the candidate complex object, and it will heapify the argument to the out-of-line call to the calc method if and when the method is ever actually overridden in practice. So the point of all this is that, the point of all this is that, you know, escape analysis has a number of tricks up its sleeve to try to mitigate situations in which escapes actually happen, even though it's, you know, the high-level description is that it's trying to detect situations in which things do not escape and trying to stack allocate those things. In fact, it's often able to stack allocate things that actually do escape and generates code that deals with them if they ever actually escape in practice. I had mentioned also, finally, that EA in some situations might decide to request another passive EA. So here's an important situation in which that might happen. While doing its analysis, EA might determine that a candidate for stack allocation can be stack allocated, but it might find that it can only be, it has to be allocated contiguously because the thing is passed as an argument. EA might actually decide not to allocate that, stack allocate the item on the current passive EA, and instead it will ask for the method to be inlined and request another passive EA to be applied after the inlining happens, so that the hope being that if inlining happens, that the next pass of escape analysis will actually stack allocate the object discontiguously this time. So looking for trying to gain extra benefit from the escape analysis. That can happen up to 3 consecutive passes at opt level hot or lower, or up to 6 consecutive passes at the highest optimization levels. Okay, so that gave a really quick overview of what escape analysis is, what it tries to do, and some of the things it tries to do when it actually detects things that escape and it would still like to stack allocate objects. Now I'm going to go on and talk about some of the recent improvements that have gone into escape analysis over the last year and a half. So one thing I didn't really highlight here is the consideration that escape analysis has to give to loops. The way stack allocation happens in EA, it will reserve one location on the stack for within a method invocation for each candidate object that it ends up stack allocating. So you can't have 2 different instances of a candidate available at the same location. So an object that's allocated within a loop has to be used only within that iteration, or else it's considered to be an escape. If you consider this Fibonacci sequence computation, within the loop, the object that I'm constructing here is going to be used, it's going to be assigned to I think I've swapped the names of the variables around here, but in any instance, there, it's available through, it's going to be available through Fib2 on the next iteration of the loop, and then via Fib1 on the subsequent iteration of the loop. So each time an instance is created, it's going to be available through the next couple of iterations of the loop. So you've got two different instances that are active at any one time within a particular iteration of the loop. Because EA is only capable of allocating one spot in the stack for each candidate, it has no way of managing the fact that this particular thing would be accessible on two iterations of the loop. Okay, but in many cases, you still have things that behave in a favorable fashion within a loop, where an object is created within a particular invocation and only used during that invocation. Or in an example like this, which came from an external benchmark, that was intentionally trying to test out how object allocation is happening in comparison to use of primitives in a similar situation. This thing is actually just constructing a result object on each iteration of the loop, and it's constructing an F object on each iteration of the loop. And on each iteration, it's only using the values of those things to feed into the value of the object on the next iteration. So there's no real overlap of the usage of these variables. And EA does have code that checks for this sort of situation, where a value that's constructed in one iteration is being used to feed into the value on the next iteration. So incrementing F or accumulating a value in result, using the current value of result as one of the things that feeds into the value. EA, in principle, was designed to be able to handle this sort of situation. But in actuality, the way the IL that's being, the intermediate representation that's being produced by the JIT is generated, it's actually copying the objects that are being allocated through several local temporaries. And the way that was being done, it ended up confusing escape analysis, and EA ended up thinking that the uses of the candidate objects were actually overlapping one another, and it thought that they were escapes. So EA was not stack allocating the F and the result objects with for the generated code of this method. But through an improvement that Vijay wrote about 2 years ago now, it goes through and treats all the copies of a candidate that has been made to temporaries as if they were equivalent to the candidate, and going through and processing the value numbers of those things accordingly and the USDEF information accordingly, it's able to detect that, in fact, there's no overlap. So the existing overlap detection between iterations that happened is now successfully handling this case. So that's a good improvement in that situation. But that same thing, that same piece of code also exposed an issue with HCR, hot code replace. So this hot code replace is a mechanism through which the implementation of a class can be replaced via the JVM TI interface. So that allows the JVM to, that allows user code to replace the implementation of a class at any time after it's been loaded, and usually for the purposes of instrumentation or perhaps debug support, those sorts of things. There's a subset of HCR. In general, HCR is allowed to make fairly arbitrary changes to the implementation of a class, but there's a subset of HCR known as fast HCR, in which there are certain restrictions that are placed on the kinds of replacements that might happen. And those include changes to the actual body of a method. So the implementation of a method, the bytecode that appears in it, can be replaced at any point during execution when HCR is enabled. But under fast HCR, no changes to the class hierarchy will occur, and no new methods or fields would be introduced. So given these restrictions on HCR, JIT compiled code will have guards inserted. It will have checks inside the generated code that check whether the implementation of a method that's been inlined has been replaced by HCR. So inlining is one particular place that's very susceptible to the effects of HCR. If the method's been inlined and suddenly the user code replaces the implementation of the method, so now the inlined version of that piece of code is no longer valid. So if it's been replaced, the JITted code can no longer execute the inlined version. In the past, under HCR, there were restrictions to escape analysis because of that. So in particular, no peeking into methods was permitted when HCR was enabled, for the same reason as inlining. If EA peeked into a method and determined that something didn't escape and stack allocated something based on that knowledge, if HCR occurred, now the information that it gathered through peeking might no longer be valid. So the way to deal with that in the past had been to prohibit peeking when HCR was enabled. But now, so yeah, that just repeats what I've just said. But now an improvement that Andrew Craig has implemented and delivered. Escape analysis will actually peek into the first level method call under HCR. So if a candidate object is passed as an argument to a peeked method and is stack allocated based on that, escape analysis will insert a heapification call that's guarded by a check of whether HCR has occurred. So if HCR occurs, and I'll walk through this example, I guess, to illustrate a little more closely what that means. So this example, the doStuff class, its run method is given a list of work items. It will create a worker object and ask a manager object to assign work to that worker. So if we focus on that doStuff class, the worker object in this context is a candidate for escape analysis. In order to allow EA to happen, we have to attempt to peek into the getTotalEffort method. And in order for EA to do that now with this improvement, it will insert a runtime check of whether HCR occurs, so that any information it gathers will not, it will deal with the potential invalidation of that information. So now, after escape analysis and peeking, the EA is able to stack allocate this object, and it will generate code that checks. Was the getTotalEffort method redefined? If it was redefined, I have the EA code, generated code, has to heapify the instance at this point, and then it can call the getTotalEffort method. So if getTotalEffort was subject to HCR, if it was redefined, the peeking might might no longer be valid, so that means the object might escape. We have to heapify the thing just in case it is going to escape from getTotalEffort. If getTotalEffort was not subject to HCR, if it was not redefined, then we won't go into this block of this guarded piece of code that heapifies. We'll still go ahead and invoke the getTotalEffort method on our stack allocated version of the worker object. So until such a point at which HCR happens and the worker's getTotalEffort method is replaced, we can still continue to use the stack allocated value. If it ever gets replaced by HCR, then we are going to heapify before we call getTotalEffort. So that provides a benefit with escape analysis under HCR, especially now that HCR is enabled by default, where in the past it was not. Something similar occurs with escape analysis under OSR, on-stack replacement. So in on-stack replacement, a method that's compiled by the JIT ends up yielding execution to the JVM interpreter. So there are two different flavors of OSR. There's voluntary OSR, which occurs if a JIT compiled method has control over the point at which it yields control. And that happens through what's called an induce block, an OSR induce block in the JIT compiled code. So when if for whatever reason the JIT determines that it needs to yield control of the execution of the method to the interpreter, perhaps because an assumption that it has made in compiling has been violated or contradicted, it has to turn over control to the interpreter so that the interpreter can continue correct execution of the method, because the JITted code can no longer correctly execute. The other situation is involuntary OSR, in which the JIT compiled method does not control the point at which a yield to the interpreter happens. The important point about OSR here is that the way the JITted code is generated, the code to deal with the possibility of OSR actually has a tendency to interfere with escape analysis. So the yield happens, as I said, while the method is executing, and the JIT and the JVM have to cooperate to reconstitute the stack frame that the interpreter would expect to be able to see at that point in the execution of the method, so that it can carry on with the execution. And that reconstitution will happen in a prepare block. So we've got two things here: an induce block where the JITted code says, okay, I have to yield control, and the prepare block in which the JIT and JVM cooperate to reconstitute the stack frame as it would appear to the interpreter. Now, that was a very sort of intense look at what OSR is all about. Now, how does that affect escape analysis? Well, going back to the do stuff class again and the run method that it contained, this is sort of a control flow graph of that method. This is what the generated IL would look like for this case. So at the entry to the method, there's a check if OSR needs to happen. And if it does, then it immediately branches to an induce OSR block. Otherwise, it begins to execute the loop that was contained in that method. And it invokes an inlined method for assign work and the worker's perform work method. And it increments the counter and goes around to the top of the loop and repeats that. But at the end of each cycle through the loop, it also checks whether OSR is needed, whether the JITted code needs to yield execution to the interpreter, because possibly the inline methods were overridden or something like that. So it has to keep checking at each iteration whether or not it needs to induce OSR. Those two induce OSR blocks that appear will throw an exception, and they end up ultimately a piece of code that is associated with the method does this preparation to switch to using the interpreter, so helping set up the stack frame that's going to be generated. Now, in the context of this method, the W that's being created right at the top of the method, the worker object that's being created right at the top of the method is, as I said before, a candidate for escape analysis. The way the prepare block is created, it appears to use that worker. And if you had a much more complicated method, there might be dozens of induce blocks, and all of them would appear to be using many different things, potentially many different candidates. It's difficult for escape analysis to determine. It basically will think that all the candidates are escaping through the prepare block. And that's what this little block says at the bottom. So with the enhancement that Andrew, with another enhancement under OSR that Andrew has made, there's a special pre-pass before EA that adds special uses to the induce blocks. And that is, if you know some of the details of OSR, it's based on OSR liveness information, and it uses that liveness information to determine which symbols actually need to be used at the point of the induce block. And further, with this enhancement, EA will ignore the prepare blocks. So what does that look like with our earlier example? Well, what ends up happening is that instead of having this control flow graph, there will be this slight difference where if you look at the bottom induce OSR block, there's based on the OSR liveness information, EA will insert a use of the worker variable, the candidate worker variable, W in this case. And as I said, it will ignore the uses that appear on the prepare. Now, the induce blocks have much more accurate information about which candidates are actually need to be used at those particular points, which candidates are actually going to be need to be stored on the stack frame that will be constructed between the JVM and the JIT for the interpreter to carry on execution. With that information, escape analysis is now able to stack allocate the worker object at the start of the method, and it introduces a heapification of the worker object at the point where OSR is being induced. So now, because next-gen HCR or OSR is enabled by default, these situations that were causing problems for escape analysis, things have been greatly improved, because now we no longer have the very pessimistic information that the prepare blocks were providing. Instead, we're able to use more refined information on the induce blocks and catch more or stack allocate more cases where next-gen HCR, OSR were applied. Okay, so that brings us to the just about the end. I will just very quickly show some recent performance results. You'll have to take these as with a grain of salt, because they were just pulled together quickly. But these results are based on a suite of EA micro benchmarks that Charlie Gracie had produced, and you can find them in GitHub at the link that appears below. But this is an example of one of the sorts of things that these micro benchmarks are doing. Like in this particular case, it's simply going through and requesting value of on a long sequence of integers and accumulating the total of all those. So attempting to see whether or not a JDK JIT combination is able to is ending up doing heap allocation and lots of garbage collection for these sorts of things, or if it's able to optimize things better. So originally, without the improvements that that I mentioned in those previous slides, we were ending up in some situations getting tripped up in an example like that through the temporary copying and also potentially through the HCR and OSR issues that I mentioned. So in particular, with the loop value of example that I had on the previous slide, we were doing about 1,700 operations per second. And with a similar example using a non-integer, some other kind of object, a my object, we were getting similarly 1,700 operations per second. With the loop improvement from VJ that I mentioned, that was bumped up in both of those cases, both with the integer object and with the my object. With the further improvement in HCR and OSR from Andrew, we got further improvements in the particular my object value of case. And there's a whole raft of these micro benchmarks, and so there are still some issues that have been detected on some of those, so there's still room for further improvement. They might be EA related, or they might be related to other optimizations, but the point is that there's been, even in in these simple examples, there have been changes over the years that have caused problems, but these improvements have mitigated those. And end up stack allocating all the objects. And just to summarize, so we found out about escape analysis, how it seeks to identify objects that can be allocated on the stack. We heard a little bit about contiguous versus discontiguous allocations. We heard about how some of the techniques EA uses to stack allocate objects even when they do escape, and some of the recent improvements that have happened in EA. And I just wanted to acknowledge that some of the content of some of the slides content came from a lightning talk on EA from VJ, and I also wanted to thank VJ and Andrew for all the knowledge about EA that they've imparted over the last couple of years, and the two of them, as well as Daryl and Yi, for reviewing and all their extremely helpful comments on this presentation. And any questions?
I do have one.
Yes.
Thank you for the talk. It was great. And you gave some examples on escape analysis. It looks like it's very closely related to range prediction. For instance, in slide 26, we give an example where 99.9% we would take a path, and like 0.1% we would throw an exception, and we could stack allocate that object. And in case we throw an exception, we just could heapify that object. Was slide 25. One
Yes.
of those. Yeah. So my question is escape analysis does use any branch prediction information, or is that even possible?
Andrew or VJ, can you answer that?
So when we're doing heapification, what we're primarily interested in is what's called a cold block. So there's a notion in the compiler. So the compiler does use frequency information to guide optimization. Now, heapification is not something that we generally want to happen. It's pretty expensive, and most of the time it's not something we want to do. So there is a notion in the compiler of what we call a cold block. So it's an additional annotation on a block, which means we never expect to run it. And we use that notation on paths that have never executed, and we use it on paths that are constructed by the compiler as fallback paths that we don't expect to run. Those cold paths are the ones that we're primarily going to do the heapifications on. But as with any optimization, yes, there's a lot of guidance based on block in terms of execution frequency, in terms of where we want to look at this stuff. But the main thing about heapifications is that they'll be done in cold blocks.
Okay, cool. Awesome. Thanks.
So there was a question on the chat from Abdul Rahman, where he was asking, would a method recompile if it peaked and peak inlined a method and then the peak method was changed with HCR? So I guess you need to be a bit clear about whether you mean peaking or inlining. So if we peak with HCR enabled, the failing side of that guard at the moment just does the heapification ahead of the call, and we won't recompile the method. We'll just do the heapification and keep running. We could insert a recompilation point there, but we don't do that today. If you inline a method and you do that inlining as part of the inlining at the beginning of the compile, the current formulation of HCR will actually put an OSR point ahead of that inline call, and we will do a transition to the interpreter that will trigger the method to be recompiled. If you inline a method as part of EA, it's too late for us to set up that transition using OSR. So what we will do is we will just call the method, and it will be a traditional HCR guard where on the taken side we'll do a call. And in that case, there will not be a recompilation. We will just do the call every time.
So is escape analysis one of the last optimizations that JIT does, or is somewhere in the middle?
It's in the middle, because escape analysis, you need to clean the program up for escape analysis. You need to normalize it and clean it up to provide the opportunity for escape analysis to succeed. But you have a number of optimizations that you want to run after escape analysis because, as Henry showed, there was an excellent example he gave where we create locals and then we want to further optimize those because we may not need all of them or whatever. Things become a lot simpler because we're not traversing through the heap. Maybe Henry, do you want to show your example and comment again? Because I think that makes it really clear.
Right. So yeah, with this example, we've got this point object that's only used in the one spot. No other thing can be accessed through the same variables, and so it ends up creating several local temporaries to represent the fields of the stack allocated object, px, py, and pdist from origin. And then after further optimization, because we're never actually using or have no need of the original px and py, they can end up being discarded. Ultimately, the only thing we're interested in was the calculation of the distance from the origin.
Oh, yeah, that makes sense. Cool. Thank you.
Henry, thanks for doing the presentation. This was really, really informative. I have a question about allocating contiguous objects. When EA does that, do we also initialize the header and the lock word, even if they are unused?
Okay, I believe the header is initialized. I'm not sure about the lock word.
Yeah, the lock word will be zeroed. It is a true object. So it has a standard header and standard layout. It's no different than a heap object at that point. It's only where it lives. So the layout of a stack allocated object. So a contiguous stack allocated object layout is identical to the layout in the heap for an object of that type. So if the heap objects have a lock word, the stack objects will have a lock word. The only time that the layout is different is if we succeed in discontiguous allocation, in which case the header disappears and we blow it apart into its constituent fields as locals.
I presume if we stack allocate, we can see all the uses of the object. If we never access the header, is there a reason why we have to initialize the J9 class, for example?
So the J9 class can still, so we can stack allocate an object that's going to be part of an instance of test, for example. So in general, in general, we will initialize that header because it's going to look exactly the same as a heap allocated object, and we will need it if we need to do a heapification. So just in general, we will write the class to it.
Okay, thanks. Another question about the heapification example. So in the cold path, we seem to call the constructor to heapify the object. How do we ensure that the constructor doesn't have any side effects? Because I presume we also have to call the constructor for the stack allocated object as well.
Right. Yeah. I know of. Again, I think I'll have to defer to Andrew again because I know I've seen code in EA that worries about potential for side effects for the constructed object or how it heapifies.
Heapification does not run the constructor. All we do is a new, which is going to allocate the memory, and then we are going to copy all the fields over. We don't actually rerun the constructor because all we're doing is moving the object, not creating a new object instance. So it's while in the Java code or conceptually you kind of think about it as a new object, it is allocate some memory and mem copy essentially the contents of the stack object to the heap and replace all pointers in the stack to point now to the heap object, so that essentially the stack object is dead. So it's like a memory move more than a allocate.
I see. So I guess a prerequisite for heapification then would be absolutely no side effects.
So there isn't that requirement because all you are going to do is new, right? So new in the sense that we're going to allocate enough space. We're going to create a block of memory, get a block of memory from the heap that is the correct size, and we are going to copy directly in the trees the fields from the stack object to the heap object. And then we will have a series of conditional tests that will test each of the stack slots that could potentially be pointing to the stack allocated object. And if they are, point them to the heap allocated object. So there's no constructor run at all. There is no, it's completely transparent from the point of view of the Java semantics. There isn't a Java method that's run as part of that. It's literally carve off a chunk of memory from the heap and mem copy the contents across. Because we're just moving where it lives. We're not creating a new one.
Yeah, so, sorry about that for the examples. I should have, I should have made the examples clearer in that regard.
Well, I mean, conceptually, that's what it is. It's just that there's a subtlety about the fact that it's actually sort of a copy.
Yep.
Okay, right. So the stack, just to reiterate, it's a stack. When we do the stack allocation as part of the main line, we would call the constructor, but then in the heapification code, we would just literally mem-copy the contents onto the heap.
Correct.
Okay, thanks. That's great. And one last question. When we do the peaking, do we run data flow analyses? And how expensive in general is the peaking operation?
Well, so peaking trees is expensive. Generating them and throwing them away takes a non-trivial amount of compile time to the point where we've recently had to do optimization in the inliner for method handles to not do peaking, right? We've created an abstract interpreter on Java bytecode specifically because peaking is so expensive. So the actual peaking itself is pretty expensive. The analysis that's run on it is roughly the same kind of cost. So it's expensive, but the win can be worth it.
Is there any opportunity for caching the results of peaking? I'd imagine the same method may be peaked during many compilations.
So there was work that was looked at one point to deal with that. The issue becomes that you then have to support invalidation of those caches with class loading and with class unloading and redefinition and all that stuff. So we haven't built the infrastructure to do that. So we'll just re-peak it at the moment to make sure that we have the most current version. So yes, there's scope for it, but it's not really proven necessary. The escape analysis itself is extremely expensive, so trying to get it into an envelope where it would fit it warm at the moment is not really something that's in this form that's practical. We have other ideas about how to do that, but I won't discuss those at the moment.
Last call for questions.
Just one more question. This should be a rare scenario. I'm just wondering if a finalized method is defined against a class, does that automatically update that particular class type consideration for EA or?
Okay, there's I know that I've seen code in EA that's dealing with the case of finalize, and I believe it ends up if it's something that can be stack allocated, will end up I'm probably going to misspeak. I know that it does some handling of finalize. Like in some situations, it will remove a call to finalize that it sees for something that's stack allocated. Now, I'm not sure if there are restrictions on that, like if it's not overriding the default finalize method or something like that. I saw this about a year and a half ago. So how about I can look into that and get back to you, Joanne.
Okay, thanks.
Thank you.
Any more questions?